Hi there. In this video, we will model real-life scenarios and real-world data using exponential and logarithmic functions, including some variations on the exponential theme, namely the Gaussian curve and the logistic curve. To start, for a warm-up, we're going to model this y equals 2 to the x, fairly basic exponential growth curve, and keeping in mind that we have a vertical scale of 2 spaces, it'll allow us to get pretty high y values without going too far off the graph. 14, 16, and we can even get up to 32 when x is equal to 5 before running out of room. And on the other side, I'm not going to plot lots of points because it gets very small very quickly. And we have our horizontal asymptote on the left-hand side of y equal to 0. In other words, as x approaches negative infinity, y approaches a height of 0 on this graph. But we have different right-end behavior, which is the hallmark of an exponential growth curve. Namely, on the right end, as x approaches positive infinity, y approaches positive infinity. So this is our basic parent function, y equals 2 to the x, and now we'll take a look at some transformations of this parent graph. In the next case, we have y equals 1/2, or 2 to the negative 1 all to the x. So we can see that this 1/2 to the x, which is a base of 1/2, which is between 0 and 1, and therefore leads to exponential decay, can also be seen as a horizontal reflection of y equals 2 to the x. In other words, every point on the y equals 2 to the x graph changes the sign of its x-coordinate. So I'm going to do a small little cheat since I have a tablet here, and I'm just going to copy the blue graph, and I'm going to reflect it. So I'm going to flip it left-right, and just make sure to match. Before I do that, actually, I want to make sure to plot a point so that I can see the anchor point, namely the y-intercept. And so when I flip that now, I know where to flip the point. I know to put that at the y-intercept. Okay, so we have our exponential growth and exponential decay curves. And they are y equals 1/2 to the x and y equals 2 to the x. Let's take a look at this next expression, and before we rearrange it, let's just recall that if we have x to the a all to the b, we can remove the brackets by keeping the base and multiplying the exponents. But multiplication is commutative, so I can multiply a times b or b times a, and then I can work backwards and pull this apart to get x to the b all to the a. So what this means is that I can swap the order of x times ln 2, and I could make this y equals e to the ln 2 times x. But then I can go from this x to the ba to the bracket version and make this e to the ln of 2 all to the x. And then what I can do with e to the ln of 2 is recognize that ln means log base e. And so this is really e to the log base e of 2. And because the e to the exponentiation base e and logarithmication base e are inverses, that just leaves me with 2. And so all of this stuff is really just 2 to the x. So the green graph is really the same as the blue graph, and I'm just going to write it here as e to the ln of 2 times x, or x times ln 2 in the exponent. Now another way that we could rewrite that is to see that y equals e to the x ln 2, I could invoke a logarithm property, and I can bring that coefficient as an exponent up on the 2. So then I could write this as e to the ln of 2 to the x. And by the same reasoning here, that e to the and log base e undid each other, I can see that e to the log base e of 2 to the x are also inverses. So e to the and log base 2 cancel, leaving us with 2 to the x, which is why e to the x ln 2 is the same as 2 to the x. So this is interesting because it just goes to show that even though I had a basic graph here with a base of 2, I could rewrite that as an exponential graph with a base of e. In fact, I could write any base that I want using a change of base, whether it's from the exponential or the logarithmic perspective. Now in the next case, I have my basic blue graph, and then I have this plus 3. To go into transformational form, that plus 3 is being done after the exponentiation base 2, so it's really being applied to the y. And so this tells me that we have a vertical translation of positive 3 spaces, which means to go up 3 spaces. So I'm going to take a copy of the parent graph, again with the y-intercept, and I'm also going to take a horizontal asymptote with it. And hopefully I'll be able to carry all of that, copy it, and let's see if I got it all. I'm trying to move it around with me, but it doesn't seem to want to go. Yeah, it did. So I'm going to take this and I'm going to move it up 3 spaces. Now vertically each space is 2, so it has to go up 1.5 grid marks. So it's a little bit hard to see, but I've got my parent graph translated vertically 3 spaces. So it's 2, 4, 6, 8, 10. So I only want to line up my horizontal asymptote 1.5 spaces up, which is actually 3 spaces, 3 units. Okay, so that's my vertically translated graph, and I'm just going to write it as y equals 2 to the x plus 3 here. The last graph I have is y equals log base 2 of x, which is the inverse graph, which has been a reflection through the line y equals x. And that means that every point on the blue graph has had its coordinates swapped. Now, I don't have a square grid here. By that I mean horizontally each vertical line represents 1, 2, 3, 4, but vertically each turquoise line represents 2, 4, 6, 8. So I have a 1 by 2 grid, which means that I can't really draw this y equals x line at a 45-degree angle, and it might not look like a real reflection through this horizontal or through this slanted line y equals x. Anyway, what I will do is recognize a table of values that if I have x and y, which is log base 2 of x, that x represents the powers, and so some of the powers of 2 that I'm interested in plotting are things like 2, 4, 8, maybe 1. Meanwhile, the exponents are the values for y, and so the exponent that I put on base 2 to get each of these powers would be 0, 1, 2, 3. So this gives me some ordered pairs that I can plot, and so I'm going to have 1, 0, I'm going to have 2, 1, I'm going to have 4, 2, and then I'm going to have 8, 6, 7, 8, 3, and I can get to 16 maybe, 10, 11, 12, 13, 14, no, I've run out of room. So my exponential graph is reflected through the line y equals x to get this logarithmic graph. And my exponential graph used to have a horizontal asymptote at y equal to 0, so my inverse logarithmic graph will have a vertical asymptote at x equal to 0. Okay, so I'm going to call this the inverse transformation, or the reflection through y equals x. So I'll just write here reflection through y equals x. In this next warm-up question, we are going to rewrite each given value as a power of 2. So what we really mean by that is to express the given value as a power which has a base of 2. So in other words, we want to change the base from the given base that we have here, so base 8, for example, to base 2. So each of these powers or values or expressions will be rewritten with a change of base. So in the first case, what we're saying is we want to write 8 as a power of 2. In other words, we want to fill in this box with an exponent. And so we can say that 8 is equal to 2 cubed. So we're really solving each of these equal to 2 to the x, and we're solving for x, or the unknown. So the next case, we want to write 1 over the cube root of 4 as a power of 2. So I don't always want to use x, especially because I see some x's coming up here. So let's use a different variable, one that won't kind of get in the way. Let's use a. And so we're really just solving for a. So just to be clear, my answer is to say that 8 is equal to 2 cubed for the first one, and I want to say that 1 over the cube root of 4 is equal to 2 to the something here. Okay, we can use the change of base, and fortunately 4 can be expressed with a common base of 2, so I'm going to get 2 squared, but then the cube root of that makes it 2 to the 2/3, but then the 1 over means I'm reciprocating the power, which means I'm changing the sign of the exponent. And so with all that in mind, we see that a is equal to negative 2/3, but I really just wanted to go from here to here. So I want to rewrite this answer as 2 to the exponent negative 2/3. So in this case, the a wasn't all that important or necessary, but it helped to give me a focus, which was to realize I wanted 2 to the something. The next case, maybe it's pretty straightforward. We can write 1 as 2 to the exponent of 0. And 9 is not a perfect power of 2, unlike 8 and 4, so we can't really work this one out the same way. We can set it up as an exponential equation, and we can solve for a. But really, a just means the exponent that we put on base 2 to get 9, and we know in one step what a needs to be. The exponent that we put on base 2 to get the power of 9. In other words, we can write 9 as 2 to the exponent that we put on base 2 to get 9. And so in order to express 9 as a power of 2, it will be 2 to the log base 2 of 9. Now when we think about that, again, this is 2 to the, and then log base 2 of something. The 2 to the and the log base 2 cancel, so 9 is equal to 9, which is a true statement. Okay, but we're really getting into the reason why we're going to do this now, because we're going to want to change the base often to base e. Base e is a natural growth value, or growth factor, for biological and chemical processes, natural processes. So we are going to rewrite e as a base of 2, and then later on vice versa. So e is going to be 2 to the something, and that something might be called a, but really a is just the exponent that we put on base 2 to get the power e. So we know that a is equal to the exponent that we put on base 2 to get the power e. So we can rewrite e as 2 to the exponent that we put on base 2 to get the power e. And again, the 2 to the and the log base 2 cancel, so that e is equal to e. Remember, if we write 2 to the as this notation so that everything's on the ground, we don't end up with the exponent floating in midair. So this e is not up in midair. It's really down on the ground, like the 9 was. Okay, well the next case is really the same thing. It's just that we have e to the x. So I'm just going to modify part e and call it part f, and I'm going to raise both sides to the exponent of x. And now all of a sudden we would multiply these two exponents, so we would have a times x is equal to log base 2 of e. In other words, we would write e to the x. Well, I think I'll put my answer here for part f. E to the x is going to be e, which is all of this stuff in red, 2 to the log base 2 of e, all to the exponent of x. And then, just like we saw earlier, x to the a all raised to the b is x to the a times b. Here we can get rid of these round brackets by multiplying the exponents. And so we see that e to the x is equal to 2 to the log base 2 of e times x. I can either put the times x at the back like this, or just to make sure that I don't multiply e and x first, because the order of operations says to perform log base 2 to e and then multiply by x. I'm going to put that x in the front. Now I'm not tempted to multiply that x and that e. Now of course we could invoke that property of logarithms where that x comes up as an exponent, and then this says 2 to the log base 2 of e to the x, which makes sense because the 2 to the and the log base 2 cancel, and e to the x is equal to e to the x. So our goal here is not to do anything to make these different, but just to express them with different bases. We want to change the base from base e to base 2. In fact, we wanted to change every base to base 2. Okay, so for the last one we want to do the same thing, but this time we have a base of 10. So for part g, I know first of all that I could write 10 as 2 to the log base 2 of, and they would cancel, leaving me here with 10. And then I raise both sides of the equation to the exponent of 10, which means that I multiply these two exponents, and I get 10 to the x is equal to 2 to the log base 2 of 10, and then that exponent is multiplied by x. I don't want to put x at the back because I don't want to think that this is 10 times x, so rather I'll put x at the front, or I can invoke that property of logarithms, which says that the x comes up as an exponent on 10, giving me 2 to the log base 2 of 10 to the x. And then by the inverse property law, 2 to the and log base 2 cancel, so that 10 to the x is equal to 10 to the x. But we are, of course, changing the base from base 10 to base 2, and so this is how we could rewrite. Either of these would be acceptable as a change of base. In number 3, we want to solve for two unknowns, a and b, such that the graph of y equals a times b to the x, an exponential growth or decay, depending on the value of b, passes through 2 points. So we want to substitute x and y, not once, but twice, to get a system of equations for the remaining unknowns, a and b. So I'm first going to substitute, I'm just going to write my model here. And my model currently is y equals a times b to the x. So the first thing I'm going to do is substitute the first point, negative 2 comma 6, for x and y, which gives me 6 equals a times b to the negative 2. Now I can rearrange that later, but for now I'll just leave it because I don't have any inspiration about what to do to rearrange it. And I substitute the other points in, and I get that 3/4 is equal to a times b to the exponent of 4. So here we want to solve these two equations for both a and b. One approach would be to rearrange each equation for a and then eliminate the a. Another approach would just be to solve one equation for a and then substitute that expression into the other. So that's what I'm going to do here. First, I will notice that this says 6 is equal to a divided by b squared. And then if I multiply both sides of the fraction by b squared, which I wanted to do in a different color, so if I multiply both sides of the equation, let's say by b squared, that will get rid of the denominator, and I will end up with a equals 6b squared. Then I can take that expression and substitute it into the second equation, the green one, where I have the value for a. So now the green equation says that 3/4 is equal to my value for a, which is now 6b squared, multiplied by b to the 4. So I can get all the variables on one side and all the numbers on the other. I'm going to divide both sides by 6, which is the same as multiplying by 1/6. On the fraction side, I want to think of multiplying by fractions, so I divided by 6, and instead I wrote it as multiplied by 1/6. So now this gives me a total of b to the 6. There's a lot of 6's and a lot of b's in this. And I can simplify the fraction on the right-hand side so that we have 1/8. Now, this is neither an exponential nor a logarithmic equation because the variable is not in the exponent or the power, but the variable b, the unknown, is in the base. And so this is the class of functions that are things like x squared or x cubed, even 1/x or the square root of x. These are all variable raised to a constant exponent. And so this class of functions is given the very confusing name of power functions. If you think about it, the exponential function 2 to the x is also a power because it's a base raised to an exponent. But we call this an exponential function because the variable is in the exponent. And the inverse of an exponential function is, of course, a logarithm. Meanwhile, when we have something like x squared or x cubed or b to the 6, where the variable is in the base, then the power function needs to be undone, or the inverse needs to be applied, for example, by taking the cube root, or by squaring, depending on what that function was. So here, we are not going to apply a logarithm, but we are going to undo the exponent of 6 being applied. So let's just rewrite that b to the 6 equals 1/8 over here. And my goal, if you keep in mind, is to get b to the exponent of 1. So I'm going to do something to both sides of the equation, which will undo the exponent 6 and get me to the exponent of 1. Namely, I'm going to raise both sides to the exponent of 1/6. Because then I multiply these exponents, which gives me an exponent of 1 on the base b. So now I've solved for b, I just need to tidy up the right-hand side. Well, another way of saying raised to a fraction exponent is to take a radical, or in this case the 6th root of 1 over 8. That may or may not be tidier. In fact, I kind of like leaving it with a fraction exponent. So if I do that, I'm going to see that I have b to the 1, and then I have, this is not just 1 over 8, but it's 1 over 2 cubed, and then I said I was going to leave it as a fraction exponent. So I could rewrite this as 1/2 all cubed, and then all to the exponent of 1/6. Now these exponents can multiply to get rid of the square brackets, and 3 divided by 6, because we're multiplying 3 over 1 times 1 over 6, which gives us 3 over 6, or 1/2. So it gets a little bit confusing because we have 1/2 to the 1/2, and that's just the value for b. Now we take that value and we back substitute it into, let's say, the red equation, and we can solve for a. So I'm going to clean up a lot of this here. I don't need a lot of this in my way. I'm just going to keep track of what the value for b was and substitute it here. And so therefore, a is going to be 6 times the value for b squared. And the value for b is 1/2 to the 1/2. Well, so that's somewhat convenient because these exponents will multiply, leaving me with 1. So 1/2 to the 1 is 1, and 6 times 1/2 is equal to 3. So I get that a is equal to 3, and b is this somewhat messy 1/2 raised to the 1/2. I suppose we could call that the square root of 1/2, which makes it a little bit easier. And even easier still, we could call this the square root of 1 divided by the square root of 2, which is 1 over root 2. So when we substitute those values for a and b, we get that our model, our exponential model, is y equals 3 times 1 over the square root of 2, all to the exponent of x. And if you're not sure, you can take a look at that value on the calculator, but we will see that our base value is between 0 and 1, and so this is going to be an exponential decay curve. Okay, so we wanted to come up with the base to be a whole number, and right now our base is not a whole number, but I could rewrite this base by changing this from 1 over root 2 to a base of 2. And if I write this as a base of 2, then I'm going to get 2 to a negative exponent because I have the reciprocal for the power, and then the square root means a fraction exponent of 1/2. So really, when I tidy all of this up, I can see that my exponential function can be written in a much tidier way. And that tidier way is to say my base is just 2, and then I have some transformations on the exponent, namely 2 to the negative 1/2 times x, or negative x over 2. So this is making it look a lot tidier. So now we want to do what we did in the previous warm-up question. We want to change from base 2 into base e. In other words, I want 2 to be turned into e to the something. So if we're not sure what to put in there, we can put, let's not use a since I was using it earlier. Let's use another letter that hasn't been involved at all so we don't get confused. Let's call it w. So we want to know what would w have to be. But really, we want e to the to cancel, and we want to be left with 2. So 2 has to equal e to the log base e of, so they cancel, and leaving me with 2. But log base e can be written as ln, so we're going to get e to the ln, or natural logarithm, or ln as I pronounce it, of 2. And so now I can replace 2 with all of this, and I can put it in here. So for part B, I would express the answer as y equals 3 to the something to the negative x over 2. And the something is going to be e to the ln of 2. Well, again, we have some exponents, and we can join these by multiplication and get rid of these round brackets. So we would get y equals 3 times e to the negative x ln 2 divided by 2. Now, I find this expression much more complicated than the one in blue, so my preference is to leave it in the blue way, but very often you will see people using base e. However, you can change bases quite easily, as we saw in the question number 2 warm-up. Just to prove that we can change bases quite easily, we now want to go from base 2 to base 10. So we are going to change base 2 into base 10. So 2 is going to equal 10 to the log base 10 of, well, and of course the 10 to the and the log base 10 will cancel, and we have to be left with 2. So I can rewrite this a bit more simply because the base 10 is the common log and I don't need to express the base. So I can take that expression and replace it for the 2 over here, which says that y is equal to 3 times 10 to the log 2, all to the exponent of negative x over 2. And again, I have an exponent here and an exponent outside the brackets. And I can multiply those two exponents together to come up with my final y equals 3 times 10 to the negative x log 2, all divided by 2. Well, it wasn't the e that made it complicated. It's this log 2 or ln 2 that makes it complicated. I still prefer the blue expression. This is the last question in the warm-up before we really get into some exponential and logarithmic modeling, but it's a nice problem and I'm not going to put the answer here just yet. In fact, I'm just going to scroll through each of the remaining slides so that if you felt you wanted to tackle these problems on your own, you can take screenshots of them and give them a try. So here's a nice problem about a particular strain of bacteria, and it's a bit of a thinking problem. You shouldn't really have to do any modeling to think it through. The next thing we're talking about then are exponential and logarithmic models. There are 4 main models, 5 if you consider that exponential breaks into growth and decay. And you can just take a screenshot of that and look through the different models, their shapes of graphs, and the circumstances under which each will be used. So the first set of problems to look through are exponential models, and the big idea here is the law of exponential change. Again, just take a screenshot if you're interested. Here are some problems to go along. So we have some investment of money. We have the depreciation of the value of a car, so it's really a decrease in an investment of money. Here we have a strain of bacteria again, and I should point out at this point that I want all of these questions to be modeled using a table of values, then plotting points on a graph so that you can see the shape, and then coming up with the algebraic model like we did when we just solved for a and b a moment ago. Then once you have the algebra equation, you can see that each question involves some information. Usually it says, here's the value for x, solve for y, or here's the value for y and solve for x. Now if we have an exponential growth or decay question, then the x represents the exponent and the y represents the power. So depending on whether you have x or y, you might need to put it in the equation into exponential or logarithmic form, depending on who you're solving for. Once you solve for values, you should make sure that those values make sense within the context of the table of values and on the graph. So an exponential decay graph, for example, will decrease as time goes on. Meanwhile, the exponential growth graph increases as time goes on. Here's another example, radioactive material. Lots of different questions and lots of ways of rearranging the algebra. Here's another problem. This one is slightly different because we have a different horizontal asymptote. I'll leave it at that. And here we have another half-life or a radioactive substance problem. It's just that the question is phrased rather differently, so you have to maybe read between the lines to get enough information to model the equation. Now we're getting into something called the Gaussian model. This is quite common for statistics. And again, take a screenshot. The video will follow up with some more information, maybe finishing this example that comes up, or you can look things up online to see what Gaussian models and what they mean. So here's an example of a Gaussian model. You'll notice that the equation is given rather than you having to come up with the model. However, if you're in a statistics class, you would probably have to come up with that equation. The next type of model or function is the logistic growth model. And this one is nice because even though we see populations grow exponentially, they don't tend to grow forever. That growth is not limited, it's not unlimited. And therefore we would use something else like a logistic growth model. So this is a nice problem to be done with graphing technology and regression technology. Now we're talking about logarithmic scale and logarithmic modeling, and I just want to point out that the reason we need a logarithmic scale is because we have a lot of numbers that are very, very large and very, very small. And when we take the logarithm of something, we're taking the logarithm of a power, which can be very large or very small, say a million or 0.000000001. And what we do when we take the logarithm of a power is we get an exponent. And those exponents tend to be more human-sized. So it allows us to talk about a number like a million, but then see that a million is 10 to the 6. And 6 is the exponent on 10 to get a million. So it's easier for us to talk about 6 because it's more human-sized. It's the numbers of fingers on our hands is 10, so 6 fits in our hands, whereas a million is quite large. And similarly, very, very, very small numbers would have negative exponents, which are still much more realistic than really, really small decimal numbers. So the logarithmic scale allows us to take the microscopic and the megascopic and place it on a more human-sized scale. So here we can talk about atoms, and we can talk about planets or stars in the solar system, and we can talk about the Richter scale, we can talk about pH of solutions, and get different examples of very, very large and very, very small numbers. Okay, so there you have it, a brief introduction to exponential and logarithmic modeling, and solutions, and another video will follow. Good luck and happy problem solving.